So for those who don't know me, I am a professor at Monash University. My name is Rob Hyndman. I'm one of the chief investigators of the Optima Training Centre. So my field of research is statistics, particularly developing new statistical methodology. And I am particularly working on forecasting topics and topics involving large collections of time series. So I've been at Monash for about 30 years. I'm also a fellow of the Australian Academy of Science and the Academy of Social Sciences in Australia, and a fellow of the International Institute of Forecasters. So let me start by sharing my screen. Okay, hopefully you can all see that okay. So I'm going to talk a little bit about forecasting from a pretty non-technical perspective. So don't expect too many equations or technicalities. I'm just going to give an overview of the way we think about forecasting from a statistical or probabilistic perspective. And I'm going to talk about my experience. I do a lot of consulting with government and industry, and I'm going to use some of the case studies I've done over the years to sort of illustrate some of the ideas here. But let's go back a long way before we do that. Let's go right back to the beginning of forecasting. And it hasn't had a great history, actually. So that's one of the early forecasting tools. It's a model of a sheep's liver. I've seen it. It's in the British Museum. And it was used by Babylonian forecasters approximately 600 BC. Most of you are probably not familiar with sheep's livers, but I believe that that's a very accurate depiction. And what they would do is the clay models were used to train forecasters in how to read a sheep's liver. And the forecasters in practice would take a real sheep's liver, which was infested with maggots, into the field with the king. And when the king wanted some advice about whether to attack a particular city or not, he would consult the carrier of the liver. And that person would look at the distribution of maggots throughout the liver to decide whether it was a good omen or not to be attacking the city. And so that's divided into 55 sections. You can see the squares there. And if maggots were in a certain section, it meant something. And if they're in a different section, it meant something else. And so that was the software, if you like, used by the early Babylonian forecasters. Our forecasters doesn't have quite as many bugs in it, at least not deliberate bugs, but we also use tools to help us do forecasting. Come forward to around 300 BC, so about 300 years later, and during the period of the Greek Empire, there was a very famous forecaster at a town called Delphi in Greece. Again, I've been there, had a look at this place. So that's the Temple of Apollo in Delphi in Greece. And that's a depiction of the Delphic Oracle, a famous female forecaster who lived at the Temple of Apollo, and people would come to her and ask, what's going to happen? Should I do such and such or something else? I'm about to get married. Is it going to be a successful marriage or anything like that? And she would actually be hallucinating through ethylene vapors that would come up through the floor of the temple because it was above a cave which had these ethylene vapors in it. And in her trance-like state, she would make pronouncements that were believed to be prophetic. Come forward a little later, one of the early Roman emperors said, anyone who consults a soothsayer on account of curiosity of the future will suffer capital punishment. So it wasn't a great profession to be in the early part of the 100 or 200 AD. And then recently, forecasters have also got themselves into trouble. The chairman of IBM in 1943 said, I think there's a world market for maybe 5 computers, which was a pretty bad forecast, even in the 1940s. Heads of computer organizations are actually famous for making terrible forecasts. The president of the DEC, which was a big electronic corporation in the US, said in 1977, there is no reason anyone would want a computer in their home, which was 3 years before IBM made the first personal PC. DEC is no longer in business. Steve Ballmer, the CEO of Microsoft, said there's no chance that the iPhone is going to get any significant market share. No chance. That was in 2007, shortly after the first iPhone came out. Again, a terrible forecast. Microsoft is not in the phone business, and there's a good reason for that. And then people outside the tech industry also make terrible forecasts. One from Donald Trump: we're going to be opening relatively soon. The virus will go away in April. He said that in February 2020. By April, there were tens of thousands of people dying in New York, and they had mass open grapes. So, forecasting can be hard, and people ruin their reputations. So let me now talk a little bit about what I think of as a forecast from a statistical point of view, and how do we think about it, how do we measure whether it's accurate, and so on. So my definition of a forecast is that it's an estimate of the probability distribution of a variable yet to be observed, a variable to be observed in the future, or at least future to the data that you're looking at. So it's a probabilistic thing. It's an estimate of a distribution. It's not a number, it's a probability distribution. To help sort of make that a little more concrete, think about this example. So this is monthly data on short-term visitors to Australia. And so you can see that over the period of the data, we have a trend that sort of slowly increases through the data, particularly towards the end. We also have some quite marked seasonality with these peaks appearing in around December every year. So you get those sort of peaks, so you get seasonality, you get some trend, and we build a model that tries to take that information and project it into the future. The model I'm using is called an ETS model, and you can generate a possible future from this model. So here's one possible future, call it future number one. I could take the same model and generate another possible future without changing anything else, the same data, the same model, but it's a stochastic model, it's a probabilistic model. So every time I generate a new future from it, it's a different future. So here's another possible future that could come from that model, and so on. And we build up, doing this lots and lots of times, we build up a lot of different potential futures, and that helps us understand what the likelihood is of any outcome over the coming months. So we take those possible futures and you can compute probability intervals based on them. So the dark blue line in the middle, let me just zoom in so you can see it a little better. The dark blue line in the middle is the average of all of those possible futures. The next, this darker shaded region contains 50% of the possible futures, and the lighter blue shaded region contains 90% of the possible futures. And you can see behind them, some of the futures lie outside the 90% region. In fact, 10% of them do. When we talk about a point forecast, we mean the average, the blue line that goes through the middle of these things. It's the best estimate of what's going to happen in the future. We don't expect the future to look like that because that's usually much more regular than any individual future could be, because it's an average. It's an average of all of the possible futures. And it gives us an idea of what's unlikely. So it's unlikely to be out here somewhere, but it's pretty likely to be in this sort of region at that time period. So that gives us an idea of where the future might be. And of course, once the data comes along, we can then have a look to see how good our forecast did. So this was a model we had for total short-term visitors to Australia. It used data up till the end of 2017. And if we look at what actually happened, the model did really well for 2 years, throughout 2018 and 2019, extremely well. The 50% region covers about 50% of the data. The 90% region covers about 90% of the data. So it's exactly what you would expect from a good statistical model. But of course, by the time we get to March or April 2020, that's disastrously bad, because the numbers of short-term visitors to Australia dropped to close to zero. The thing is, our model was based on the history of the data set, and it replicated the history continuing into the future. And of course, if the future is not like the past, then the forecasts may not be good. Amos Tversky, a famous behavioral economist, said, "He who sees the past as surprise-free is bound to have a future full of surprises." And it's a good lesson that whatever forecasting model we have, it's built on some data and some assumptions. And if the data doesn't contain the types of patterns we're going to see in the future, or if the assumptions we make are no longer valid in the future, then the forecast could well be wrong. We don't expect the forecast, even when it's good, like in this period in here, even when the forecast is good, we don't expect the forecast to exactly measure what's going to happen. It's more containing the observations with specified levels of certainty and where you know the likelihood of it being in different regions of the space. Okay, so what can we forecast? People try to forecast lots of things, some of them more successful than others, and some things are much harder to forecast than other things. And sometimes people call something a forecast when it's clearly not a real forecast. So this is an example of that. This is from the Commonwealth government, and it's showing what they claim to be forecast of the cash balance every year from 2011 to 2017. So the actual is in black and their forecasts are these coloured lines at the top. And clearly they're overestimating the cash balance every single year. And that's because these are not really forecasts. These have a political purpose, and I would never call these forecasts. I would call them hopecasts. It's what people hope what might happen, but they're not genuine forecasts, and it's clear that they're not, because a genuine forecast is going to be, above the actual 50% of the time and below the actual 50% of the time. People try to forecast the weather and do so increasingly successfully. The current weather forecasts are unbelievably good compared to what they were 20 or 30 years ago. People try to forecast exchange rates or stock markets. So there's some stock market data, exchange rate data, very hard to forecast both of those. One of the things I've done, and I'm going to talk about this a little bit, is forecasting pharmaceutical sales. And I'll show you how we did that. Forecasting electricity demand is an important area, particularly in planning future supply. Forecasting COVID, I'm going to talk about that as well. Forecasting tourism numbers, so that's down near the Great Ocean Road, and its area of popular tourism. And tourism numbers are something that I've spent quite a lot of time forecasting over the last 25 years. I'm not going to talk about it today, but you saw a little hint of it in the example I was using before. In fact, my colleague George Athanasopoulos and I were actually contracted to forecast Australia's tourism numbers, and we got a contract in December 2019, and we started working on it in January 2020, and then we realised that with clearly COVID was happening, and whatever we built on the historical data was going to be inaccurate. So we actually developed some methods that worked, that built in the assumption of a pandemic and did not just rely on historical data. So here's a bunch of things that people try and forecast, and I want you to just spend 30 seconds thinking about which of these is the easiest and which is the hardest. Can you put them in some kind of order to what's the most difficult and what's the easiest to forecast? So things like what I've talked about: stock prices, exchange rates, electricity demand, pharmaceutical sales, but also astronomical things like Halley's Comet, time of sunrise, and so on. So how would we order them? So if I was doing this in a class, I'd let you all come up with your own order and then we'd compare them. But let me just skip that and go straight to what I think is a good order for these. And that's like this. The easiest on that list to forecast is the time of sunrise this day next year, even though it's a long way away and it's a daily forecast. It's such a predictable event that it is easy to forecast that. Another astronomical event, Halley's Comet, is also pretty easy to forecast if you know enough about astronomy. Then meteorology is actually pretty straightforward. Maximum temperature forecasts are usually pretty accurate. Then followed by electricity demand, retail sales, and the hard ones are stock prices and exchange rates. And they're just ordered there by how far away they are. So stock price tomorrow is much easier than stock price in 6 months' time. Exchange rate in a week is a little more difficult than stock prices tomorrow. Why that order? You might think that makes some intuitive sense, but can we put some science around it? So we've come up with some factors that describe when something's easy to forecast. And so here are the factors. Something's easier to forecast if you have a good understanding of why it varies the way it does, so what contributes to it, and can you measure those things? If there's lots of data available, if the future is somewhat similar to the past, and if the forecast cannot affect the thing you're trying to forecast. So if you think about those 4 factors and think about what was on my list back here, time of sunrise this day next year. We have a very good understanding of how that works. So number 1, yes, we know about that. There's plenty of data. The future is extremely similar to the past, and the forecast can't affect what you're trying to forecast. Like what you say about the sunrise next year is going to make no difference at all to what time it actually rises. So all of those conditions are met. It's a really easy thing to forecast. Whereas you look at the bottom of the list, Google stock price in 6 months' time, we don't have a good understanding of the factors that contribute to it. There's a lot of psychology and sort of inherent uncertainty in stock prices that's difficult to measure. There is plenty of data though. Number 2 is not a problem. The future may not be similar to the past. It may be, but events may happen over the next 6 months that could cause the future to be different from the past. And the 4th one is also not met. The forecasts can affect the thing you're trying to forecast. If someone well-known makes a forecast about the Google stock price, it can have a direct effect on the stock price itself. So some of these factors are not true for the ones lower down on my list. Okay, so I'm going to do 3 case studies from my own consulting practice over the last 20 years or so, and show how these things come into play. So the first one is PBS expenditure. So PBS is the Pharmaceutical Benefit Scheme. That's the sale of drugs through pharmacies around Australia. And it's a subsidised scheme. When you go to the pharmacy, you're not necessarily paying full price for the drugs that you purchase. They're subsidised to allow more equitable access. And so the cost to the government depends on how many of different types of drugs people buy. And that's not known in advance, so it has to be forecast. And it costs a lot of money. It's about 1% of GDP is spent on this. So the total cost is budgeted based on forecasts of drug use. Now, I got involved with this about 20 to 25 years ago, around the turn of the century. And when I got involved with it, this was what the ABC website looked like. And this was one of the headlines on it, May the 30th, 2001. Opposition demands drug price restriction after PBS budget blowout. And you look down here, the budget blew out by almost $800 million. So that's a lot of money, even for a government to find. And it happened twice. Happened in 2001, happened again in 2002. And after it happened the second time, someone from the Department of Health in Canberra called me up and said, "We have a problem, can you help?" Actually, maybe the first time was 2000 and the second time was 2001. And then I got this phone call. And so I asked them to explain what they did. They said, well, at that stage, it was $4.5 billion for the budget. So the under forecasting by $800 million is a seriously bad forecasting error. They had thousands of products, seasonal demand, subject to lots of covert marketing and uncontrollable expenditure and volatile products and all sorts of weird stuff going on. They had monthly data for 10 years, which sounds pretty good. Like that's more than 120 observations on thousands of products, but they said they didn't know how to deal with the seasonality. So they aggregated it to annual values and they weren't sure about the quality of some of the recent data. So they used only the first 3 years of data, at which point I was a bit mind blown that you would be trying to forecast these sales using 3 years of data, 3 annual observations from 7 years earlier. And I said, well, what do you do? How do you do the forecast? They said, we use the forecast function in Excel, which just fits a straight line. So I said, well, I can do better than that. It didn't really matter what I did. I was going to do better than that. So here's what we did. We developed a class of models called ETS models, which are now probably the most widely used sort of off-the-shelf forecasting models in the world. But they were developed for this project. And here's some examples of PBS data using more recent data than that initial project. So this is, one example of a product with not much seasonality and a decreasing trend, and there's the forecasts from my model. There's another one, strongly seasonal, increasing trend, and the forecast much tighter because it's a stronger pattern. This is a really strange product which dropped to near zero and then increased again, and this period was probably due to some products coming off the PBS for a while and then being put back on. So the forecasts are much wider because of the uncertainty. There's another one with these big jumps. You can see all sorts of weird stuff going on in the data set, and the model needs to be able to deal with that. So we developed this model for completely automatic to adapt to such changes, adapt to changes in seasonality, adapt to level shifts and changes in trend, so that it could be run automatically, so that whoever was doing it in the Department of Health didn't need to know what was going on. They could just be able to run this as a black box. And it reduced the mean absolute percentage error from nearly 20% down to 0.6%. So instead of being out by $800 million, it was out by around $10 to $20 million. Gave them prediction intervals to get a sense of uncertainty. We published it, and it's now implemented in many, many software packages, including the forecast package that I wrote for R, the Fable package that one of my PhD students is involved with, and other commercial software. If you've ever done a forecast in Tableau, it uses my code and it uses the ETS models to do so. Excel eventually came out with a function called forecast.ets, but as is typical with Microsoft, especially with Excel, they implemented it so badly it's actually not the ETS model at all, it's something else. So PBS was actually pretty straightforward to forecast once you had a decent model, because you've got trend and seasonality, which you can easily model. There's a fair bit of data there. The future is not always similar to the past, but we used a very adaptive model so that was not so much of a problem. And the forecast can't affect the thing you're trying to forecast, at least not easily. I mean, if we were forecasting enormous amounts of expenditure, then the government would probably change the PBS scheme, and then that would obviously affect what's going on. But would have to be quite extreme for the forecast to affect the thing we're trying to forecast. Okay, let's do another example. This is peak electricity demand. So I got involved with this also not quite 20 years ago. Again, somebody called me up and said, we have a forecasting problem. Do you think you can help? This person was from the South Australian electricity market operator in the days when there were state market operators. There's now only a national market operator. So back then in 2006, he said they wanted to forecast the peak electricity demand in a half-hour period, so half-hourly forecasting, but for 20 years' time. So it's an enormously long way in the future. And he had 15 hours of half-hourly electricity data, lots of temperature data and some economic and demographic data. And he said that South Australia had the most volatile electricity demand in the world. Sounded like a fun problem, so I said, sure, let's have a look at it. And although it sounds like ridiculously impossible, and certainly going 20 years probably was impossible, but going even 2 or 3 years ahead is not that difficult, because of the very strong signal that occurs in the relationship between demand and temperature. Going more than 2 or 3 years away in a forecast horizon is problematic because technology changes so much. Think about electric vehicles being charged overnight. We wouldn't have had that in our model in 2006. Just to show you what the data looks like. So this is Victorian statewide demand, and you can see that there's a lot of volatility around summer, and then you get this increase in volatility in winter, but less sort of crazy, not the same peaks. If I zoom in a little bit, you can see that there's a time of week effect, which looks like a little hard to see there. You can see it over here. So you see this one, that's their weeks, and you can see, so it's down on the weekend. So there's a weekend, there's a weekend, there's a weekend. It's down on the weekends, it's up during the weeks, and these little individual spikes, they're days. You've got a time of day effect, you've got a time of year effect, you've got a time of week effect. These big spikes are when you've got a heat wave. So it's 4 days of very hot weather, cause a lot of air conditioning and therefore a lot of demand. You can see that because here I'm plotting the same data against the temperature, and you can see days above 40 degrees, 4 in a row. If I look at demand as a function of temperature, it's not linear. You get an effect from cooling and you get an effect from heating like that. So it's a V-shaped function. And it's different on work days and non-work days. And in fact, it's different at different times of the year. So let me just show you how it varies during the day. So that's midnight. And we're going to just run the time forward half hour at a time. And so it's at its lowest around 2:30, 3 o'clock in the morning. And there's not much difference between working days and non-working days. But then as the morning progresses, you see them separate out, because on work days, there's a lot more power early in the morning. People get up earlier, they go to work. Buildings, workplaces turn their lights on, turn the heating on or the cooling on. And then you can see the shape of the non-linearity changes through the day as well. It's more non-linear in the middle than it is during the night. And these big peaks are happening in the late afternoons, around 4 o'clock, 4:30, on the hot days. And then as it gets later in the evening, the peaks drop off. The blue and the orange get closer together because people are doing more similar things during the evening than they are. And there's a slight weird thing happens just around midnight, and then back to the start of the day again. And the same pattern repeats. So any model that we build for this has to take into account, whoops, what's happened? Lost my plot. Let's go back. Okay, any model that I build for this has to take into account all of those calendar effects: the time of day, the day of week, the time of year. Is it a holiday or not a holiday? What's the current weather conditions, and not just the current, but the recent, because of thermal inertia in buildings. If it's been hot for a while, you use more air conditioning than if it's just become hot. If you're going far enough ahead, we need to take into account climate change, any demand response incentives from the energy suppliers, changing technology, more efficient air conditioning, for example, or electric cars, and changes in economic and demographic changes. So we built a model to do all of this, and particularly for long term, that is more than a few weeks ahead. And that model is now underpins all of the long-term peak electricity forecasting done around Australia by the Australian Energy Market Operator. They've adapted it and modified it and extended it since this work, but it's essentially the same thing going on underneath. EDF in France also uses the same model, plus a few other energy companies around the world. Again, we can do this because we have a pretty good understanding of what's driving it. It's largely around temperature. There's lots of data. At least in the short term, the future is similar to the past, up to months ahead. Once you get to years ahead, of course, the future might be different from the past. And your forecasts can affect the thing you're trying to forecast with demand response. So if the energy company thinks there's going to be a lot of demand, they might put it in place, higher prices or some other demand response policy to try to mitigate it. But apart from the extremes, the forecasts don't really affect the thing you're trying to forecast. Let me give my third example, which is to do with COVID-19, the most recent of my 3 examples. So the first ones were from 15 to 20 years ago. This one is from the last few years in forecasting COVID-19 cases. And as with most of my forecasting, it started with someone contacting me to say, can you help? And that person was contacting me on behalf of the Australian Health Protection Principal Committee, which was the key decision-making committee for national health emergencies. It's been in operation for years and years. It wasn't just for COVID-19, but it was the committee that sort of took charge of the COVID-19 pandemic and was the sort of the body through which forecasts were relayed that then went to health officers and the Australian Chief Medical Officer. There were lots of people on this group from lots of different places. I've only got some of them there. I didn't have room for all of them. But if you heard of the Doherty forecast, then this was the same group. There was a couple of them from the Doherty Institute who happened to be the leaders of the group, but most of us came from elsewhere, including some of us from Monash and some from Melbourne. So what we started doing this in March 2020 and continued. In fact, we're still doing it to some extent. We continued officially working for the federal government until December 2023, so nearly 4 years. And we're still doing it in a less official capacity, but also providing forecasts for flu and for RSV. And the same group is now about to morph into an NHMRC Centre for Research Excellence called a CEFA, Australian Centre of Excellence for Epidemiological Forecasts and Analytics. So for this purpose, we had case level data of every positive COVID-19 test, which back in, for most of that time, 2020 through to 2023 was pretty good data, at least for the first 2.5 years. We also had daily population mobility data from Google, Apple, and Facebook. We had contact survey data, so we could have some idea how much people were mixing. And we had case numbers from lots and lots of other places from the Johns Hopkins COVID-19 repository. So all of that data went into a range of different models. This is what the case numbers looked like. This is on a log scale because the major outbreaks dwarf the other outbreaks if I put them on a regular scale. So this one here was sort of the first major outbreak in Victoria, which led to our first lockdown. Then these ones, so this was New South Wales and Victoria, sort of towards the end in the second half of 2021, changing variants meant that there was another outbreak, and then it got quite bad at the start of 2022, and then it sort of declined after that. And it's still, I'm only showing you data to November 2022, but we are still looking at data like this. There were lots of problems with the data set, and so a lot of estimation went on to try to reconstruct what the numbers really were because of incomplete testing or delays in reporting or various other things. So what do? We built 3 different models. One was a classic epidemiological model called a SEIR model. That was the one that the Doherty Institute with people at Melbourne Uni were responsible for. There's another one called a generative model, which some people from University of Adelaide were largely responsible for. And there was another one, which was a global autoregressive model, which those of us at Monash were largely responsible for. And they were built using very different types of mathematics. So one was around sort of modelling how people move between groups from infected to exposed to recovered. That's the SEIR model. One was trying to simulate individual behaviour. And so it was trying to sort of model the way people interacted as individuals. And then ours didn't try to do anything in terms of the epidemiology of it. It simply tried to fit the patterns, but using not just Australian data, but data from every country and region around the world that we could get our hands on. And we just fitted one model to all of that data after doing a little bit of cleaning to get rid of some weird stuff. And it turned out that that worked pretty well. So it's a global autoregressive model. And then we put them together to form an ensemble. So each of these models generated possible sample paths, and then we combine the sample paths and we get an idea of the probability distribution reflected in the combination of models in a process known as linear pooling. And then that was the way we got the probability distributions that were then fed to the federal government and various chief health officers. So this process works best when any of the individual models is not really capturing all of the information. They're all a bit overconfident and they're using different data sources. So we thought it might be appropriate to do it in this context where we were all trying to use slightly different data sets and combine different ways of thinking about what was going on. Just to show you what some of the forecasts look like. So this was forecast in late 2020 for Victoria after the 2020 peak. And you can see that the forecast was actually pretty good for this period. That was in a bit later in the end of 2020. That's partway through 2021 where we missed the start of an outbreak. As you can see, these intervals, I should have said, these intervals are 50, 60, 70, 80 and 90% intervals. So this was part of the 10% of possible futures that was outside our 90th percentiles. That was in 2021 and so on. So you can see the sort of things that we were producing and then they were being fed through to various government bodies who needed to make policy decisions. Again, thinking about the forecastability factors, we have a pretty good understanding of the factors that contribute to what's going on. We didn't have necessarily lots of good data. I mean, by the end of 2020 and partway through 2021, we did have really good data. But at the start of 2020, we didn't. We had very little history. And by the, well into the pandemic, the data quality was dropping off considerably, which made forecasting a little harder. But there was plenty of data. It just wasn't necessarily good data. The future was definitely not similar to the past, even within the pandemic, because variants kept changing, and so our models had to keep changing to adapt to them. And the forecasts were affecting the thing we're trying to forecast, because if we were forecasting numbers going up considerably, then that could lead to a policy change, greater restrictions on movement, etc. And so that was not met. So this was quite a challenging thing to do. So there's 3 case studies from my consulting work and give you some idea of the types of things we think about and how you might present those forecasts. Now, I just wanted to touch on 1 or 2 other things before I open it for questions. Firstly, how do we actually measure, how do we actually assess whether those prediction intervals are any good? So let me go back to the example I started with, where we had 50% and 90% intervals, and we had some data that did well for a while and then didn't do so well. So in principle, a 90% prediction interval should contain the actual values 90% of the time. So you just look at whether those 90% intervals contain 90% of the values. You count what proportion of actual values occur within the 90% intervals. So you can see in this example, you've got some points that are just getting outside. That one's just outside the 90% interval, and so is that one. The rest of them are inside the 90% intervals, and so that's about 90% of the time. Second thing is a good prediction interval will be as narrow as possible. So you don't want to have hugely wide intervals, even if they have the accurate coverage. You can do that, for example, by having all of the points falling outside the interval on one side of the interval. You can still get the right coverage, but you can have enormous intervals, and that's not particularly helpful. So a good prediction interval is as narrow as possible while retaining the coverage. And you don't just want to do it for 90% intervals. We want to do this for all possible intervals, and not just 50 and 90, but every possible interval you can imagine. You want these properties. It has to contain the right proportion, and it has to be as narrow as possible. And so there's this whole area of statistics called probability scoring methods, which measure across all possible prediction intervals and balance the calibration, that is it got the correct coverage, and the sharpness, that is it as narrow as possible. And so it balances these 2 things, and it comes up with a numerical score. And you try to minimize that score And if you've come up with some intervals that have a better score than some other set of intervals, then they're in principle better intervals because they're both calibrated and sharp. So one of the, I'm not going to give the equations for it, but one of the scoring methods that is in quite wide use is called the continuous ranked probability score, CRPS. It's the one we used throughout the pandemic when we were trying to measure how good our forecasts were. And so here's the sort of graphs that we would produce. So this is for weekly forecasts created between the 17th of September 2020 and the 15th of June 2021. We're producing, we produce forecasts up to about 4 to 6 weeks ahead. For this graph, I'm just showing you the first 20 days of daily number forecasts, and for 4 different states. So if you just look at New South Wales, for example, the global AR model, which is the one that we did at Monash, is this green line, was not so good because it's got larger CRPS than the other 3. The generative model, which is the one from the University of Adelaide, did really well, particularly for the higher horizons for this period. The SCIR model is this pink one. And then the ensemble, which combines all 3, is the orange one through the middle. So you can see that the SCIR model actually did quite poorly here and here in Queensland and South Australia for this period. The global AR model was the worst for New South Wales, but it did pretty well everywhere else. The generative model did quite well, except in Victoria, and it didn't do so well there. And so that's why we always like to use an ensemble, because it balances out. It's somewhere in the middle. It gives you a good range of coverage of what's going on. So that's how we measure or assess forecast uncertainty, to make sure your intervals are as uncertain as they should be, but not too uncertain or too confident. Last thing I want to do before we open for questions is to talk about the future of forecasting, since my topic was forecasting the future and the future of forecasting. So I just thought I'd make a few comments about some general questions. And I'll get these questions every time I give a talk about forecasting, so I might as well head them off. The first one is, well, what about neural networks and deep learning? I haven't talked about those. Certainly, some of the most recent deep learning models, particularly those using transformers, have been extremely good. But until about 3 years ago, any of the neural net models or deep learning models were considerably worse than the statistical models. There's been many forecasting competitions over the years, going back about 40 years to the first forecasting competition. And at least since about 1998, neural networks have been contributed to these forecasting competitions. So people, the forecasting competition usually consists of lots and lots of time series that you have to forecast, and people submit their forecasts, and then they are assessed based on how accurate they are compared to the truth. In 1998, neural networks did appallingly badly, just absolutely awful. Even using just the most recent observation as your forecast would have done better. In the later competitions, they got better. In the one that was held, when was it? It was about 2018, I think. The best 2 methods, the method that came best used a combination of statistical models with some neural networks built on the top of them. So it was like a hybrid, and it did quite well. And then there was another competition in around 2020. The neural nets didn't win that one, but they were sort of at least competitive. And then in the last 2 or 3 years, there's been some really good work done around neural network forecasting, particularly using transformers, that now looks like it's beating, with sufficient data, that it's beating most of the statistical models, but it does need a lot of data. There's a method called TimeGPT built on the same transformer technology that is behind ChatGPT. It's called TimeGPT, and it's currently the best of the models built on that type of architecture. And if you applied it to the data from the competitions from 20 years ago, it would have won it hands down. So it's there's been a lot of progress in this space, but it's quite recent. And I expect over the next few years that the models built using transformer architecture will probably become much more widely used, and in most cases will beat the type of statistical models that we've used historically for the last 50 years. Will we ever be able to forecast black swans? Well, no, by definition. So a black swan is something that you've not seen in historical data and that you do not expect to see. There was a phrase coined by Nassim Taleb to describe something that is totally unexpected that happens because it's not been in your data set. And black swan refers to the English explorers arriving in Australia, thinking all swans were white and coming across some black ones, which they hadn't imagined or seen before. So obviously you can't forecast something that you have not seen and that you cannot imagine. We can try to forecast things that we have not seen but that we can imagine, but we're not using data-driven models then. You're using more judgmental adjustments or other types of judgmental models. But certainly, my forecast for tourism numbers that were made in 2020 for the next 5 years did not use, because they were done in the context of COVID-19. They were not just using historical data, they were judgmentally adjusted, and they've proved extremely accurate. But so it depends what you mean by black swans, but if it means something you haven't seen and cannot imagine seeing, then of course not. Does more data mean better forecasts? No. Often there's two problems. Often more data might be poor quality data. Good forecasts are built on good quality data. And sometimes you're better off using less data, but better quality data. And sometimes if you're using data that has from a long time series, the oldest data may not be so useful for forecasting what's happening next. So you need to make sure both the data is good quality, but that it's still relevant. Will AI take over forecasting? Well, probably it'll take over most things. I see it as a tool of forecasters, and that forecasters will use AI tools just like in every other area of life. We are learning and will continue to learn to use AI effectively. So take over in the sense of there not being any jobs for forecasters? No. But take over in the sense of it being another tool in your box and you'll use it a lot, then yes, that will happen and is already happening. And are there many jobs for forecasters? There are an astonishing number of jobs for forecasters. And often what happens is somebody has a degree in statistics or a degree in data science. They'll go to their first data science job and they'll be asked, like, could you do these forecasts? And they will not know how to do it because they haven't learned how to forecast. It's not something that's on the curriculum of a lot of universities, but it's one of the most common things people get asked to do when they become data scientists, because it's one of the most common things that companies want done with their data. What's going to happen next? So I wish more universities would include courses on forecasting. But for those that end up in this position and want to know, well, what do I do? I don't know how to do forecasting and I've not learnt it, but I've got to do it. I'm going to suggest two things. Firstly, let me just switch my screen to, not there. Hang on. Firstly, this book. So this is my online textbook on forecasting principles and practice. It's entirely online. It's freely available, and it contains lots of sort of practical advice about how to do forecasting, how to use the models, and so on. This is built around R, and all the R code is included in the book, so you can easily replicate it, and lots of practicing forecasters use it. Okay, so this is atex.com/FBP3, and as I said, freely available, go to it. The other website I wanted to point you to is forecasters.org. If you find yourself doing forecasting, you really should be a member of the professional institute for forecasters, the International Institute of Forecasters. I've been a member for more than 25 years. It's an exceptionally good professional body. They have great conferences, great journals, and if you're doing forecasting for a job, you should be part of it. Let me go back to my slides. Hopefully they'll show up. So let me finish by just showing you where to find more information from this talk. So the URL at the bottom is where you can get the slides from, and those addresses are where you can contact me. And for your attention.